In this video, we're going to take a look at hypothesis testing for means for a right-tailed test. Previously, in the last video, I said it would be one-tailed, but it's taking a little longer than I thought. So this one is going to be right-tailed, next is left-tailed, and then two-tailed. So again, we've looked at all of the parts of hypothesis testing, and there are three basic steps. The first is to state the null and alternative hypotheses, and also make sure we know which distribution we're using, the normal distribution or t-distribution, and then the level of significance, which should be given in the question. Step 2, gather the data, which is really just going to be reading the question, and then calculate the necessary sample statistics, and that will include a test statistic and a p-value and a critical value and whatnot, and then to draw a conclusion and, most importantly, interpret that decision. In addition to those steps, we're actually going to include a step 0, which is to make sure we check the appropriate conditions. So we should have been checking those as we were doing the confidence intervals previously. So we're just going to add that as a step here as well. For each of the videos for Chapter 10 and Chapter 11, I have included a page that looks like this, and this should be a very good reference page, so feel free to screenshot this page, as this is all of the information that you need for hypothesis testing for means where sigma is known. Step 0 is to check the conditions. Is it a random sample? Is sigma known? And is n greater than or equal to 30, or the population distribution approximately normal? So same conditions that we checked previously. Then we're going to state the null and alternative hypotheses. In this case, because sigma is known, we will use a normal model. And then, of course, we're going to use the given level of significance. Then we're going to gather the data. So the test statistic is a z-score, x bar minus mu, so observed minus expected, over the standard deviation, divided by the square root of n. Remember that I call this the standard error. Your book does not call it that, but many books do call it that. The critical value for the rejection region, and the p-value. So what we're going to do is we're actually going to find both of these values, both the critical value and the p-value. And typically we're going to make our decision based on the p-value, but we're just going to find both of them because it's good practice. And bonus, the critical value that we find is the same critical value we're going to use for an interval, which we'll talk about more in a little bit. And then we draw our conclusion. We reject if p is less than alpha or the test statistic is in the rejection region, or fail to reject if p is greater than alpha or the test statistic is not in the rejection region. So again, you're going to see a similar slide as we go through the remainder of these videos with the appropriate items changed. We're going to look at our first example, and as we're reading through this question together, I am going to simply jot some things down that we'll be using as we go forward. So the State Education Department is considering introducing new initiatives to boost the reading levels of fourth graders. The mean reading level of fourth graders in the state over the last 5 years was a Lexile reader measure of 850 Lexiles. So remember that whenever it gives us a value that says, hey, here's what it has been, here's the status quo, we know that that's going to end up being our null hypothesis. And then the developers of a new program claim that their techniques will raise the mean reading level of fourth graders. So again, it's claiming that the Lexile reader measure will increase, so greater than 850. To assess the impact of their initiative, the developers were given permission to implement their ideas in the classrooms. At the end of the pilot study, a random sample of 1,000 fourth graders, so n, the number of samples is 1,000, had a mean reading level of 856. So 856 is our observed, which we use x bar. It is assumed that the population standard deviation is 98. So 98. And we're going to use a level of significance of 0.05. So that's all of the basic information that we need going forward. So hopefully that made sense. Technically, I'm going to do this step on the next page, But again, it's good to have all of this information. So let's get started on our hypothesis test. So that I didn't have to recopy the entire 2 paragraphs, I really am just going to put a summary now at the top of each page. So it's the same summary that we just found together. And then I included that the developers claim that it's going to raise the mean reading level because technically we haven't written our hypotheses yet, which we'll do on this page. So first, check the conditions. Yes, it was a random sample. Unfortunately, I didn't have room to recopy everything, but it does say in the actual paragraphs that it was a random sample. Sigma is known. It's known to be 98. And n is greater than or equal to 30. Obviously, yes, n is 1000. So my conditions are met. Step 1 then is to state the null and alternative hypotheses. Now, again, we talked about this on the last slide where we had all of the information from our situation. But in the past, the Lexile measurement has been 850, so we assume it will continue to be 850. The alternative is based on the claim that the techniques will raise the mean reading level, and that's why we're using greater than. We think that 850 is going to increase. The next step is to gather the data, which is obviously mostly calculations, and then calculate the necessary sample statistics. So I've recopied the summary at the top, including the null and alternative hypotheses. There are 3 things that we're going to find: a test statistic, a critical value, and a p-value. The test statistic, for any time we're testing one sample with means where sigma is known, will always be this formula. X bar, which is observed, minus expected of mu, divided by the standard deviation, divided by the square root of n. One thing I do want to point out, and we'll talk about this when we get to the Excel page, is if I'm doing this in Excel, I'm going to make sure that I'm diligent about where I put my parentheses, because I see a lot of people correctly put 856 minus 850 in parentheses in the numerator, but then they say 98 divided by 98 divided by the square root of 1000, which is fine, except they forget these parentheses and then they get the wrong solution. So just make sure that you are smarter than Excel and you know how to calculate it correctly. The critical value for the rejection region and the p-value. So again, what I'm looking for a critical value and the p-value has everything to do with my alternative hypothesis and the direction that it goes. So in this case, we have a critical value for a right-tailed test. So if you'll recall, we have our little curve, and what we're saying for the critical value is we need 0.05 to be to the right, because it's a right-tailed test pointing to the right of our critical value. So we need to find what's this value right here. If this is 0, how many standard deviations to the right? So how do I do that? Well, if 0.5 is to the right and Excel only calculates to the left, as we should know by now, that means I have to take 1 minus alpha for this right-tailed test. So 0.95, because that's how much would be to the left of my critical value. So 0.95, which gives me 1.645. So that says 1.645 is my critical value. And just a preview, obviously we'll talk about this on the next page, but if our z-score is in the rejection region, so think about 1.645 and then 1.936 is to the right of that, obviously this should be a conclusion to reject the null because it's in the rejection region. But again, we'll talk about that on step 3. The other part of step 2 is to find the p-value. The p-value is essentially saying what is the probability, if it were true that the Lexile reading measure is still 850, what's the probability that I would find a sample of 856? And so what I do to find that is, again, using my z-score. This is to the right, so it's 1 minus norm S dist and then 1.936. Because normestist of 1.936 finds the area to the left. I want the area to the right, so 1 minus. And that's where I came up with this value. Again, as a preview to what we'll talk about on the next slide, P, which is 0.0264, is obviously less than alpha, which of course tells us to reject the null, which is what we said with the rejection region as well. So again, based on everything that we have just found, we should be rejecting the null. So notice both the critical value of 1.645 and then the z-score of 1.94 being in the rejection region, and the p-value of 0.0264 being less than alpha, both tell us to reject the null hypothesis. So again, our conclusion should include, here's the data that we used, here's the decision that we made, here's what it means. With 95% confidence, or sometimes you'll see with 0.05 level of significance, there is evidence to suggest that the mean Lexile reader measure will increase. So again, where did that come from? If we reject the null, there's evidence that the alternative is true. So there's evidence that mu is greater than 850, or in this case, that the mean Lexile reader measure will increase from 850. Now my favorite part's coming up because I'm going to show you how to use Excel to do all of this for you. But before we do that, I really want to talk about corresponding confidence intervals because this can be a little bit tricky. So when we created confidence intervals previously, we always said, hey, if alpha is 0.05, then I'm creating a 95% interval. And technically, yes, that's cool, but here's the problem. What I have here is I have my normal model, and again, we have this 1.645, and I have found some value that's in the rejection region, so we're rejecting. What I want to do is find what's the interval of things that I can expect based on a one-tailed test. So if it's a one-tailed test, which is what we're learning about in this video, then we're always going to take 1 minus 2 alpha to find what confidence interval, what percent confidence interval we want. Now, if that gets confusing, here's the really good news. All we're going to do is take whatever critical value we used when we found the rejection region, we're going to use that to find the interval. So what is the formula for a confidence interval for means where sigma is known? That is x bar plus or minus our critical value, which is z alpha over 2. Well, we're just going to put z because it's not really alpha over 2 anymore. And then the sigma divided by the square root of n. So all I've done then is plug all of those values in. Again, do all of this as one calculation or let Excel do the work, which is what we're going to do in a moment. And then I find my interval. And here's what the interval means. We're 90% confident that the average Lexile score will fall between 850.9 and 861.1. Again, remember that our our test was testing 850. If I had this on a number line, 850 would be here, and then 850.9 would be to the right of that. So this is the interval, and notice 850 isn't in it. So that supports rejecting the null hypothesis. So that's how, again, you will write your conclusion if you have to also do an interval, which of course you will for your project. You will include an interval, and then you will say, here's what I expect to happen in context, and then does the hypothesis value fall in the interval, and what does that mean, reject or fail to reject? Now, I know this video is a bit on the longer side. I'm still hoping to get under the 20-minute threshold, but no promises. Let's talk about how to set up Excel, and this is for either one-tailed test. So this is going to cover right-tailed test, which is what we're doing now, and also a left-tailed test. So again, what I'm going to do is in Excel, I'm going to have some input boxes, and these are things that I'm going to enter myself. So let's just make them green for fun. These are the values that I'm going to enter. And then I'm going to let Excel calculate the z-score, the critical value, the p-value, and even the conclusion, the margin of error, and the interval. So let's talk about how I set this up. Remember that a z-score is just using the z-score formula, and the z-score formula says take x bar minus mu divided by sigma divided by the square root of n. So that's all I've done in Excel. If I point back to that cell, you can see I've taken b2 minus b1, x bar minus mu, divided by, and then very important parentheses there, b3, so standard deviation, divided by the square root of the sample size. So it's going to calculate the z-score formula for me based on that formula. And then we're going to look at the critical values. So we know that a left critical value is going to be a negative critical value, and a right critical value will be a positive critical value. So again, if we think about this, the left critical value is going to be somewhere over here, which is negative. And then the right critical value is somewhere over here. So what do I need? I need alpha to be to the left of that. So norm S inverse of B5, which is alpha. Or for a right-tailed test, I need alpha to be to the right of that, which means 1 minus alpha will be to the left of it. So that's what I've done here, 1 minus alpha. So those are going to be the two critical values, one positive, one negative. The p-values will be based on our z-score. So remember, our z-score is just going to be norm S dist. So what is the probability that our z-score is? If it's left, I want less than, so that's just norm S dist. And if it's to the right, I want the complement of that, 1 minus norm S dist. I'll come back to the conclusion in just a minute. E, which is our margin of error for when we're creating our corresponding confidence interval, is going to be F2, which is the positive critical value, because we want our critical value to be positive when we're finding our interval. Otherwise, these two values are in the wrong order. So just use the positive critical value, and then remember it's just, let's see, z times sigma divided by the square root of n is how I'm finding that margin of error. So that's all I've done there is F2, which is our critical value, and then sigma divided by the square root of n. For our interval, where is our interval centered? Always at the sample. So this is B2 minus the margin of error, and then B2 plus the margin of error. The last thing I included, which is just if you're an Excel dork like me, so if you're not an Excel dork, feel free to not include this. I went ahead and put in a conclusion, and a conclusion just uses an if-then statement. And in Excel, that means if something is true, then this is what to enter. And if it's not true, then this is what to enter. So all I did was I used the fact that we want P less than alpha. If P is less than alpha, then we reject. That's the fact that I used here. So I said, if E3, if my p-value, which is right here, is less than alpha, then what? Then write reject. Otherwise write fail to reject. So again, just a little Excel nerdery for you if you would like to do it. Let's go ahead now and enter in all of the values and make sure that they match up with what we just found by hand. So 850 is the hypothesized mean, 856 was our sample, 98 was sigma, sample size was 1000, alpha 0.05. And again, this was a right-tailed test, so I'm only worrying about this column right now. And what we find is a z-score of 1.936, which matches what we found previously, a positive 1.645 for my critical value, a p-value of 0.0264, and supports our decision to reject the null. And then of course we have our interval, which matches the interval that we found previously. Next, we're going to take a look at another one-tailed test, which is a left-tailed test. You'll find that most everything that we do is exactly like what we did in this video.